Okay, so what I want to skip to first, and this is this I think one of the topics that people have trouble with on this unit, and also I think your first lab after your exam will be on this, so I want to make sure I get to it. Okay, that's the timing of these things. Okay, so how long does it take to put energy on these capacitors? How long does it take to get them off? Right now, there is no impediment to the flow. And so basically, right now, it's approximately instant charging. So as the circuit currently stands, it will basically charge like that. And in fact, we've already had this discussion previously. We talked about that a conductor is an equipotential, right? So if you have a piece of conductor, you're not going to find one voltage on one end and another on the other end, right? I think in your mapping lab, right, you had that pair of salad tongs, right, and you touched all the different parts of the conductor and it's all the same voltage. That's what you have with conductors. Let me point out that this is all one contiguous piece of conductor, right? So this should very, very, very rapidly become the same voltage. So there's nothing really to stand in the way of the charge just surging almost instantaneously onto these plates until it's full. But, number one, there's no such thing really, as we've learned, as a truly perfect conductor, at least not at room temperature, no superconductors. There's always some resistance involved, right? And that resistance is going to get in the way of charging instantaneously. And I should also point out that the fact that it might take time to charge is a feature, not a flaw. So this is the first time where we've had circuits where something will happen over time. So it's a way of introducing timing into a circuit. Any electronic device that has something that has to happen not instantaneously but happen over time, a capacitor is involved. Okay? So for instance, your windshield wipers, right? Your windshield wipers, you want to be able to control the timing of them, right? There's a capacitor that's used to do that, okay? We're introducing something that will allow the evolution of the circuit with time. So let's start looking at those. And again, the way that we're going to introduce some timing into this is by introducing a resistor. So if you introduce one or more resistors, we know that current can't just surge through a resistor. It takes, there's some obstruction there. So we're looking at something called RC circuits. These are circuits that have both a capacitor that you're either trying to put energy onto or take it off, and then you have a resistor that stands in the way to prevent you from doing that instantaneously. Okay? I think what I'm going to do is I'm going to start with the easier one and then move on to the harder one. This is going to be the discharging circuit. So the discharging circuit, at some point in the past, I've managed to charge up a capacitor, and now I want to get the charge and energy off of it. So here's what I have. Plus Q, minus Q, and these are going to be the initial values. So I've charged it up at some point in the past, and now I want to use that energy. So I'm going to let these two re-equilibrate back to neutral, but I'm going to have them do it through a resistor. This is a capacitance of C and a resistance of R. So let's go ahead and start kind of telegraphing the situation. Q, let's see what happens with the charge on the capacitor, each plate. Let's see what happens to the voltage drop across the capacitor. Let's talk about what happens with the voltage drop across the resistor, and the current, and potential energy, I guess. And I guess the power dissipated through the resistor as well. This is basically all the quantities that we might be interested in. All right. So the charge starts off with some initial value. But then what happens is these positive charges are not going to hang around near each other now that they have an escape route. And that escape route is, of course, that these positive charges can repel each other, flow through the resistor, and wind up over here. But what happens when a positive charge flows from one plate and goes to the other? Well, they neutralize, right? And if we let all the charges do this, what's the eventual charge we're going to have on each plate? 0. So this runs down from a charged plate to just 2 uncharged plates. There's no charge on either plate at the end. Now remember that as goes the charge on the plates, so goes the voltage, right? That's the whole deal with the capacitor, is that the charges create the voltage. So if the charges go away, what happens to the voltage? You can't create a voltage difference with no charge, right? Remember, as goes Q, so goes V. So whatever the voltage difference is initially, whatever this is, VC initial, eventually it goes to nothing. Okay, let's go to the resistor. Initially, why does anything flow? Of course, it's because this is the higher voltage region than this. So we really only have 2 equipotentials in this whole circuit, right? So initially, the voltage drop across the resistance is whatever it is, but these are really one and the same thing, right? If we drew one of our voltage waterfalls, it looks like this. These are one and the same thing at all times. So the voltage drop across the capacitor is the voltage drop across the resistor. Another way that you could do it is by doing a Kirchhoff's loop, like we talked about last time, right? Effectively, there's no difference between how you do a loop for a capacitor versus a battery, right? If you go from the lower voltage to the higher voltage terminal, you'll get a voltage gain. When you go with the current, you'll get a drop. So that looks like this. Plus VC minus VR equals 0, which of course is just another way of a mathematical equivalent to that, okay? So really, it's a bit silly. These resistors are the same, or these voltages are the same. So these are actually, this is actually the same thing, right? When we talk about the voltage drop across the capacitor and the voltage drop across the resistor, we're talking about the same voltage difference, okay? Okay. So, initially you have a voltage drop across the resistor, so are we going to get current flow when we first connect it? Yeah. So there's going to be an initial current. But later on, when there is no voltage drop anymore, are we going to get current just for funsies? No, right? There's no motivation anymore to go across the capacitor or across the resistor, then nothing will flow for free. And again, the reason I put these two next to each other is as goes one, so goes the other, Ohm's law. If you have a lot of voltage drop available across a resistor, a lot of current will flow. If you provide the motivation, current will flow in response. Likewise, in this case, as the voltage drop gets less, the current gets less, and at the end, the voltage drop is 0, so the current is 0. Okay? So nothing flows at the end because everything's done flowing, right? Once all of the positive charges have flowed from here to here, nothing happens anymore. So you can kind of think of it like this. If this is the voltage waterfall, The only difference between this and hooking it up to a battery is that a battery has an internal mechanism that can regenerate or that can create more charge to maintain the voltage difference. So if you have a 9-volt battery, for a long time it can stay 9 volts. And that's because of an internal chemical reaction that can maintain that. There's no chemical reaction going on here. So if you have charge, pre-existing charge, however much you've put on here, that's what creates the voltage difference, and as those charges flow off, the voltage difference drops. And so what happens here is that this difference is always decreasing, okay? So it's like a time-evolving waterfall, okay? So think of it like a waterfall where the drop is made out of sand or something like that, and the sand eventually gets worn away and the waterfall goes away, okay? So once the charges have flow off, it's not an inexhaustible supply. Now obviously even with batteries that have internal chemical reactions, they only last for so long because they only have so much inside them to make that, so many reagents inside to maintain that. But here, a capacitor, you just have access to the charge that have been put on there, that's all you have, and the charge flows off, and that's kind of it. Okay, so let's talk about potential energy. Obviously, whatever amount of energy you have stored flows off. What becomes of the energy that was stored on the capacitor? Heat, right? It gets sweated out through the resistor. So it gets sweated out to the environment. It does it more at the beginning when the current is larger. And then, of course, the rate at which the energy gets dumped to the environment at the end goes to 0 because, of course, there's nothing to dump anymore, right? So basically, in this circuit, everything runs down to 0, and at the end you have a neutral hunk of stuff. You have 2 neutral plates connected by a resistor. So hopefully, this is why this is the easier case to start with, because everything runs down from whatever initial values it's been set up as, all the way down to 0. And now all we're going to do is take a look at the equations for this, okay? Because as we will find out, this is not a steady or linear progression. At first, you can imagine these positive charges are very, very, very excited at the prospect of repelling each other, right? So we have that it happens rapidly at first, but then once there starts to be a lot less crowding here, that slows down to a trickle, okay? So we have that a lot happens at first, so we have a larger rate toward the beginning, and then it gets progressively to be a slower rate by the time we approach the end. It's not a smooth progression. It actually turns out that the rate is proportional to the amount of charge. So if you have a lot of charge left, the rate at which that charge will flow off is larger, and if the amount of charge you have left is very small, the rate at which it flows off is very small as well. It slows down to a trickle. Now you can actually show mathematically that any time the rate of the discharging, or whatever, the rate is proportional to the amount you have left, this leads to a particular mathematical expression, which is called an exponential. Okay? This, conceptually, the rate being tied to the amount, leads naturally to what's called an exponential function. That's why they're so prevalent in nature. There's so many different applications of exponential functions, this just being one of them. It happens anytime that the rate is tied to the amount itself. So the rate is high when the amount is high, the rate is low when the amount is low. Okay? Now obviously this is in calculus class, so I'm going to have to basically say this statement will lead to this equation, and let me just give you the equation. So this is an equation which you will find on your equation sheet. You can just use it. have to derive it. All I'm going to do is I'm going to take this equation and I'm going to talk about its features, especially for those of you that may not be that comfortable with exponentials. Let me review a little bit. Now before I even tackle this thing with all the bells and whistles, let me just remind you of good old y equals e to the minus x, which is probably how you've seen exponentials. Is there anyone who hasn't seen this here? How many people have seen this in math class? Okay, good. So what does this look like? It looks like this. Y versus x. It drops off steeply at first, and then of course it gets closer and closer to 0. Y gets closer and closer to 0, but it never really gets there until you wait forever, right? It's what's called an asymptote. What's the value right here, by the way? What's the value of y? It's 1, right? Y at, so if you take e to the minus 0, well, anything to 0 is 1, right? And by the time you get to x equals infinity, well, that's 1 divided by a gigantic number, so that's basically 0, right? So this function basically just curves starting at a y value of 1, but you have to go all the way to x equals infinity before it drops down truly to y equals 0. Is that familiar? Okay. Now, one of the things, of course, is that if you want to talk about how rapidly this thing falls off, you can't say how long does it take to get to 0, that the answer is always infinity. So one of the other things that you can talk about is what's e to the minus 1. So what happens when we're at x equals 1? Well, that's 1 over e. E, this is a number, right? It's a transcendental number. It never repeats and never ends, right? Its value just goes on and on, okay? There's the first however many digits. If you want to impress somebody, you can remember the 2.7, and it's 1828 twice, and then a 45, 90, 45 triangle, okay? And that's all I have memorized, okay? So it's just shy in physics, okay? We say it's just shy of 3, okay? That's close enough. So this is approximately 1/3. If the exact number is about 0.37 roughly, okay? Or I shouldn't say exact number, but it's very close to about 0.37. So at this point, what happens is you're at 0.37 of your previous value, and you've dropped, of course, 0.63. So if you start at 1 and you drop 0.63, you're at 0.37. This is often the way that exponentials are judged against each other, because, of course, if you want to talk about how long does it take to drop to 0, the answer is always forever. But we can talk about the 37%, 63% benchmark, okay? Now, when you express it in terms of percentages, it sounds kind of weird. Why would you want to say, why would you want to talk about the 63, 37% benchmark? Well, of course, it's not really so odd, because 37% is 1 over e. So that's when the original value you started at has been cut by e. Okay? So those are the different features of the exponential that I'm going to rely on here, because my function here for the charge is just bells and whistles with that. So let me draw my charging function. This is a charge as a function of time. And by the way, for those of you that may not be comfortable with function notations, this is charge as a function of time. I don't mean charge times time, okay? Like that's like in math class, if you see function of x, you think it's f times x. No, that's not what it is, okay? So this is charge as a function of time. So first of all, the exponential is multiplied by q initial in the front. That just simply makes sure that instead of starting at 1, it'd be weird to always start at 1 coulomb, we start off at q initial. And then it goes from there. So we see that the charge, whatever its initial value is, it'll be excited to run down at first, and then it'll slow to a trickle later. That's what we kind of said should happen. So let's talk about what tau is. This other variable here, obviously we have kind of the exponentials that has some stuff going over there. So let's ask what happens at t equals tau. If I plug it into the formula, q at t equals tau, well that's q initial e to the minus tau over tau, and that's e to the minus 1. So tau represents the time at which the initial charge has been cut by e. So in other words, is 37%, 0.37 to 37% of its initial value. So when time tau has passed, we have 37% of our initial charge because we've lost 63%. So tau is a way of controlling the fact that not every circuit is exactly the same. Tau determines what is the time that this particular circuit takes to reach the 63%, 37% benchmark. Okay? And that's how we judge all of our exponentials, because if we asked how long does it take to discharge completely, the answer is actually infinity. We'd have to wait forever for the last tiny little drop of charge to fall off. So we can't do it that way. So instead what we do is we ask, how long does it take to reach this particular benchmark? Okay? So tau is the time it takes to reach this 63, 37% benchmark. And this is where I'm going to have to tell you, this again falls out of the derivation, maybe for those of you that are in the supplement, maybe Adam will do it for you, I'm not sure. But you can find out, the thing that it determines how long it takes to reach this benchmark is actually determined by the resistance that you're discharging through and the capacitance that you're discharging from. Believe it or not, an ohm times a farad is actually a second, okay? If you work out the units of ohms times farads, those are composite units. I think they're even composite units upon composite units, but if you work it all out, it comes out to be in seconds. So I guess Usain Bolt runs the 100-meter dash in about, 9 ohm farads? I think it's about right. Okay. So, because of course I just pulled this out of thin air, let me motivate for you why this makes sense. If the resistance that you're discharging through is larger, it takes longer to hit this benchmark. Does that make sense? Yeah, you're discharging through a more obnoxious obstacle, so it's going to take longer. So you have to discharge through a larger obstruction, discharge through larger obstruction, so it takes longer to hit your benchmark. Takes longer to hit benchmark. It also tells us that if the capacitance is larger, it also takes longer to hit your benchmark. So why does that make sense? Well, if you're discharging a really good storage device, it's not that bothered by having all this charge on it, right? So these charges are hanging out here luxuriously. It's not really that bothered by being near each other. If you had a capacitor that was really bad and all those charges were really penned up in there, they'd want to rush off. But if the capacitor is better, it's not that bothered by discharging. And so it's going to take longer, and of course, again, to hit your benchmark. So here you're discharging a better storage device. So those are the two things that go into whether it's going to take longer or shorter to hit this particular benchmark. Are you discharging a better capacitor through a larger obstruction? Well, it's going to take longer. So this is how we judge circuits off each other. Maybe another circuit, it looks like this. It also is an exponential. It also takes forever to empty completely, so that's not a useful point. Everything takes forever to empty completely. But it takes much longer before we hit the 63-37% benchmark. Why is that? Maybe you're discharging through a larger resistor, maybe you're discharging a larger capacitor, maybe both. For some reason, R times C is larger, so it's going to take longer to hit this benchmark. Okay? So this allows for the fact that even though everything takes forever to empty completely, some things will empty very slowly in comparison, right? At every point, the red line is higher than the black line, which means that at any given time point, there's always more charge on the red capacitor than the other one, right? The line that represents another circuit, this red line that represents another circuit, it's always more full at any given time. Okay, so that's the first function. And I guess let me give you a few brief words on how you might solve it. So one of the typical homework questions might be, like just as an example, what is the time it takes to be, say, 1% of the initial charge? That might be like a proxy way of asking how long it takes to empty, because of course it takes forever to empty completely. But let's say when it has 1% of the charge remaining, for our purposes that's close enough to empty. So how might we do that? Let's take the equation. First of all, work smarter, not harder. Okay? You want the charge to be 1% of the initial. So that's what goes in on that side. If someone expresses it as a percentage of the initial, they've done you a favor, because check this out. If you put in the other side, the initial charge cancels. So now we solve for t. Well, we have the time, but it's in the exponential. Does anyone remember the inverse function to the exponential? What do you do? What is it?
Log.
Log. Which log?
ln.
Natural log, that's right. Natural log of e to the whatever is pulls it down from the exponent, right? Those are inverse functions, just like tan and inverse tan, or square and square root, right? You get back to square one, right? So I take the natural log of both sides, and then over here, I managed to pull down from the exponent. Now, one reminder, when you're taking the natural log, make sure that you have the exponential cleanly, okay? It shouldn't be e to the x plus 1, right? It shouldn't be like, this is not what you want to do, okay? Don't do that. You need to cleanly isolate the exponential before you take the natural log. So I'm home free here. I get t equals negative tau ln of 0.1. You can put in whatever tau is. That's just r times c. If you're bothered by the negative sign in the front, you think, what, negative time? It's not negative. Natural log of 0.01 is also negative, so that negative cancels this negative. No worries, you have a positive time. Okay, so that's one, just a little reminder on how to manipulate natural logs. Okay, so that's the charge function. And with that already, we can go ahead and figure out another function, because once we have the charge function, multiply it by c and you get your voltage function. So you're good to go. So remember, as goes Q, so goes Vc. These two are stuck together, they only differ by a constant. So if I want the voltage as a function of time, I take the charge as a function of time and just divide by C. So I don't need to give you every single function, I only need to give you a few of them, and then the rest of them fall right out. So let me go ahead and put that in. That is going to be Q initial e to the minus t over tau, and then I'll put the c with this one. What's like Q initial over c? So if the voltage in general is Q over C, what's Q initial over C? It's V initial. So the voltage function across the capacitor, that also is a dying exponential. It starts off at whatever the initial value is and then just dies off. Looks exactly the same. Okay? If you want to draw it, it looks like this. That's the initial, and then it dies off with time. Just like we said it would. We've got the first two down. We've got this, check. We've got this, check. All right. Oh, and we actually have one more. We can do the potential energy function. The potential energy function, we said that that was 1/2, well, let's say 1/2 CV squared. That's probably the easiest one. Because then it's 1/2 times C times the voltage function we just got squared. So what is that? That's 1/2 C V initial squared exponential what's this quantity in the front? 1/2 C V initial squared. It's PE initial. And we get, once again, some kind of exponential function. The fact that it has a 2 in it doesn't really matter. It still dies down to 0. The fact that there's a 2 in the denominator does affect what tau means, but the general gist is still the same. So we've got PE, we're done with that. And then, for the other three that we haven't yet talked about, all of those, the charge is not involved, but the current is. Okay, so here I'm going to have to give you a second function to tell you what goes on with the current. And again, this is sort of pulled out of thin air for you guys, but same thing. So those are the two functions that I'm going to give you, the charge and the current. The current, also an exponential, also runs down to 0. Same deal. Current starts from the initial value. It runs down to 0, and when you have t equals tau, that's your 37%, 63% benchmark. And then from that, everything else will fall as well. So I just gave you the current function, so that's done. And then remember, Ohm's law says, as goes the current, so goes the voltage. So if you want the voltage function, you take the current function and just multiply it by R. So let me do that. I'll throw it in there. Let me throw the R toward the beginning so I can group all the constants together besides the exponential. What's I initial times R? It's V initial across the resistor, which again, I'm not really bothering to label because in this particular circuit, the voltage, there's only one voltage. We already said right here, these voltages are the same thing. We get the same function as over here. So the voltage we already knew ran it down to 0. And then if you want the power law, well, guess what? Power equals I squared times R. You just put it in there, same thing. Okay? So you can see if I am going to be willing to give you two of the exponentials, Q and I, all the rest of them just fall out. You can do any of the other ones you want. Okay? So we've done them all now. They're all exponentials. They all decay to 0 from their initial values. That's kind of it. All right? Are there any questions on this? Okay, so I guess in the next 5 minutes, let me see how much headway I can make with the charging one. Okay. So you guys will be trying both of these out in lab for the next lab experiment, which will be a week from Tuesday, a week from your exam. And so I want to get you guys prepped up with plenty of notice. Let me see how far I can make it with the charging circuit. So I have my battery. My battery is going to act like the pump. I have a capacitor that is initially empty. So I guess I should write these down. Let me see if I can do them in the same order. Q, BC, BR, I, PE, and P. So let's make some predictions here. The capacitor is going to start off as empty, and then it's going to end up as full, at least as full as this battery can make it, right? The energy stored on it will go from nothing to full, whatever the this battery is capable of making it. But it won't happen instantaneously, and it won't happen instantaneously because there's a resistor in the way. It doesn't matter if you put it on this side or this side, because remember that the entire system senses what's present. So the resistor is a bottleneck on either side that will prevent it from charging instantly. Okay? What happens with the voltage across the capacitor? Well, remember that these two stick together. Whatever happens with one, it happens with the other. One grows, the other grows. So what's the initial voltage drop across the capacitor when it's empty? 0. And how much voltage is it possible to get across by the end? The battery, right? The battery is the thing that's going to be charging it. So, and I guess let me go ahead and also remind you that these two always go together. So the resistor and capacitor are in series. So there's actually going to be 3 distinct equipotential regions in this circuit. This one, let me label it as lowercase a. This one, which is my lowercase b, and this one, which is my lowercase c. And here's what's going to happen. If the battery sets a fixed amount of voltage difference from top to bottom, and we can drop from regions A to B to C, first across the resistor and then across the capacitor, but this voltage waterfall is going to evolve with time. And let me give away the punchline, I'll come back to this next time. This voltage difference and this voltage difference are not constant. We just saw that the battery, as it charges, it takes more voltage drop, so this is actually going to have to increase. Well, if that increases, then it crowds out the other one. So this is going to decrease. So this middle step is actually going to drift, and it turns out that it drifts. It starts off at the bottom and then winds up all the way at the top. So B starts off aligned at the bottom with C and winds up aligned with A at the top. And we'll take a look at that in more detail. Let's leave it there for today, and we'll pick up on Tuesday morning. Okay, so here's what we're working on. It's the charging RC circuit. So we're going to charge a capacitor, put some charge in it, put some energy on it. But we're going to go through do that using a battery, but we have a resistor in the way. The resistor can be either before or after. Remember, the whole system senses how much resistance is there, and it will be the charging process will be slowed down accordingly. And so we've kind of started filling in some of what happens, and we'll kind of, course, just finish this right now. So first of all, the capacitor starts off with no charge, and then eventually it will reach some full charge, which we'll find out what that is. And it'll, of course, go from having no energy when there's no charge on the plates to having whatever full amount of potential energy is on there when we're finished charging it. And the, of course, as goes the charge on the capacitor, so goes the voltage. So if you put more charge on a capacitor, there'll be a larger voltage drop across it. Initially, if there's no charge, then there's no voltage drop. And at the end, and I'll go over this again, we'll find that the voltage drop is the voltage drop across the charging battery. So that's the most voltage you can get to. Other things we'll fill in, of course, here, the voltage drop across the resistor, the current, those two always go together by Ohm's law. So what happens if one grows, the other one grows, if one shrinks, the other one shrinks. And of course the power dissipated as well. Okay, so how much energy do we dump to the environment through the resistor during this process? So I've gone ahead and circled, there's actually three distinct equipotential regions here, A, B, and C, because these are in series, the resistor and capacitor in series. So generally speaking, you have this fixed voltage drop, or this fixed voltage of the battery that acts like your pump, and you generally will drop some of the voltage across the resistor, some across the capacitor. In that sense, it looks very similar to just two resistors in series, which of course, that's something that we've already talked about quite a bit. But as we will see, introducing the capacitor makes how these two voltage drops are split with each other. It makes it evolve over time. So here's what happens. At first, there's no charge on the capacitor yet, so it has no voltage drop. So there's no voltage drop from here to here, which means that there is no voltage drop between B and C. Well, if you don't drop the voltage across from B to C, it has to all be, of course, be dropped through from A to B. So initially, it looks like this. So all the voltage is initially dropped through the resistor because the capacitor doesn't yet have any charge, so therefore it doesn't yet have any voltage difference. So I can write down here VC is equal to 0. There's no voltage drop across the capacitor. I can even label my equipotential regions. A is the highest, B is the lowest, but at this point B is merged with C. There is no voltage difference between B and C yet, because there's no charge in on the capacitor. Okay? So then the charge starts to flow, they start to accumulate on the plates, and as the charge accumulates on the plates, the voltage starts to accumulate as well, and of course, there's only so much drop to go around, so the sum of the two drops has to be this fixed battery voltage. So what happens is, as this starts to increase, this starts to decrease. So basically what we have is that B is creeping upward. So what happens is, as more and more charge builds across the capacitor, it starts to accumulate voltage, and that crowds out the voltage of the resistor. And B climbs all the way from the bottom here, where it's merged with equipotential region C, the lowest voltage equipotential, it climbs all the way up until it's actually merged with A. Okay? So at the end, this will be during the process, but the end of the line, the final, or full, will look like this. So now all the voltage drop is across the capacitor. So equipotential region A is still the highest, C is still the lowest. Those don't change, by the way, because those are the battery terminals, right? Those A and C are the high voltage and low voltage terminals of the battery. It's B, though. B that's floating, and it can change. So B starts off aligned with C, then it grows as the charge flows on the capacitor, its voltage grows, and then at the end, we're going to find it's gone up and merged with A. So now the voltage across the resistor is 0. Okay? So basically, the fact that the capacitor is charging means it takes more and more of the voltage drop until it takes the whole thing, and the resistor is now not doing anything. It has no voltage drop. So we go back over here. Initially, the voltage across the capacitor is 0 because the charge is 0. What's the initial voltage across the resistor?
The battery.
The battery. Okay. But by the end, the capacitor has grown to take all of it, so you can see that here, right? The capacitor takes all of it, and the resistors take in none. Okay? So they just basically switch roles. Okay? Initially, all the voltage drop is across the resistor, and at the end, it's all across the capacitor. In the charging process, they'll both take some. Okay? But it's just that the voltage across the capacitor here is increasing, and that's crowding out the resistor, so that's decreasing. So, initially there is a voltage drop across the resistor, so of course if you supply a voltage drop available across the resistor, current will flow, right? So we'll have some initial current, but remember, as goes the voltage across the resistor, so goes the current, right? The only reason that a charge flows across a resistor is when it has motivation to do so. That's a requirement, right? So if the voltage drops across the resistor, current will flow, but now we don't have any, right? There's no voltage drop across the resistor. What's the current going to be? 0. Exactly. So that must be, that by definition, the end of the line, right? If no more current flows, then that's as much charge and energy as the capacitor is going to get, right? Because if the current stops flowing, that's the end of the line for that capacitor. Okay? Question?
Could you also say that the initial current is going to be the maximum current?
Yes, absolutely. It just shrinks down from there. That's right. So the initial current, that's the biggest it's ever going to be, and then it starts shrinking to 0 at the end. And you can think of it conceptually, right? If B is the same, grows to be the same voltage as A, why would charge go from A to B when there's no advantage to doing so? If you go from A to B, and B is the same voltage as A is, why would any charges burrow through that obstruction if they don't get a reward, right? So that's pretty much it. And by the way, the power dissipation, we can look at P equals I squared R, for instance. Of course, we'll dissipate the most power through the resistor at first because the current's the largest. And of course, at the end, when the current actually stops flowing, then the resistor won't sweat out any more energy, right? I guess while we're at it, we should probably point out, we can actually calculate Q full, what's the full charge. We can calculate the, what else do we have? Initial current. We can calculate PE full, and we can calculate P max. Okay, these are all things we can find. Well, the general formula for Q is C times V, and now we know what is the voltage of the across the capacitor at the end. It's the battery voltage, right? So that's the most amount of charge that you can get on here with this battery, right? The most you can do is to charge this capacitor up to the same voltage as the battery that is connected to. So that's as full as it's going to get, okay? Well, what's I initial? I is V over R. What's the initial voltage across the resistor? The battery. Remember that at the beginning, the battery takes it. So that'll be the maximum current. It'll just decrease from there to 0. But at the beginning, the only thing holding back current flow, remember the capacitor is completely empty, open for business, okay? There's nothing on it yet. The only thing holding back the current flow at this point is the fact that there's a resistor in the way. And you have the full voltage drop of the battery across the resistor at first. And so that's the most current that you're going to get. This is also the maximum. So notice that the capacitor gets more and more charge, most charge at the end, but the resistor gets the most current at the beginning. And of course we can use these, Q full, you can use for PE full, just use whichever formula you want. 1/2 Q squared over C, for instance. And of course what you put in is the Q full. So you put in 1/2 times Q full, and you get 1/2 C. Well, that's kind of dumb. Well, I don't know why I did this. This is stupid. Well, it's not wrong, but I should have just used 1/2 CV squared, right? So that's the alternative formula for potential energy, right? 1/2 CV squared, and then I just put in what's the final V? Well, it's the battery EMF, right? And then that, of course, is the maximum. That'll be at the end, because at the end, the capacitors where everything's going on. And then the power max, I'm not going to make the same mistake here. I'm going to use V squared over R, okay? That's one of the 3 forms of the power law. And what is the maximum voltage across the resistor? The battery EMF, right? And it happens at the beginning, okay? So at the beginning, you're sweating out the most energy through the resistor. And then as you progressively go through and charge this thing up, eventually the capacitor fills up, hogs all the voltage drop, it has the most charge, most energy stored, and then that's all that this battery can do. This is the maximum that that battery can put on that capacitor, because the current eventually goes to 0, which means nothing more is happening. Okay, are there any questions on that? Okay, so that's the general character of the answer. And again, as you can probably guess, this does not happen linearly, it happens exponentially, because it's one of those classic situations where at first the capacitor is really excited to fill, right? It's got lots of empty space, and then it becomes progressively harder to add that last extra drop of charge. So these are all exponential. And I'm going to have to, again, pull out the bare minimum of formulas for you guys to do this, and then the rest of them you can get yourself. So, for instance, let me tell you the current function. This current function is exactly the same as the current function in the discharging. It looks like this. I versus t starts off at your initial value and eventually dies to 0. In both the discharging and charging, the current runs down to 0 because at the end there's nothing left to do. In the discharging circuit, there's no more current because the capacitor's finished emptying. In this case, the charging circuit, the current goes to 0 because it's finished filling the capacitor, right? At some point, there's nothing left to do. The capacitor's either done emptying or done filling, so that's why the current function is the same. The current runs down to 0 in both cases, okay? The tau is exactly the same. That's convenient. Tau is R times C. It's the resistance that you are charging through and the capacitor you're trying to charge. And same deal with tau. That's often how we evaluate these because of exponentials that take forever to finish exactly. It takes forever technically to fill just because it gets progressively harder to squeeze on the last little bit. So we judge circuits by tau, which is again the time to drop to 37% of your initial value, having already dropped, of course, 63%. So what can you do with this? Well, of course, once you have the current function, you can get the power function because it depends on just current. It's current squared times R. You can get the voltage function because again, as goes the current, so goes the voltage. So I guess we can find that out here real quick. The voltage across the resistor as a function of time will be this function times the resistance. We can group these terms that are not the exponential. And what is that term in parentheses there? What's I initial times R?
Voltage.
That's the initial voltage, which is, by the way, is what?
E.
It's battery EMF, right? So this function looks like this. So if you wanted to plot what does the voltage across the resistor look like, at the beginning it takes it all, but at the end it takes none. Okay? Just like we said. All we're really doing it is giving it a time axis, right? So we already said that the battery voltage is entirely across the resistor at the beginning and then not at all at the end. And this is just putting it to time. It's an exponential function. So this stuff's pretty familiar. But definitely in the last circuit, everything looked like this. Everything looked like an exponential that ran down to 0, but clearly something else is needed for some of this stuff because some of this stuff grows, right? It grows with time. And this exponential in its raw form does not grow. It always goes to 0. So here's where I'm going to have to hand you one more function. That's the charging function here. So let me tell you what that is. And again, this is just something that you can get off the formula sheet. It looks like this. It's got a few more bells and whistles. It's got a 1 in there, 1 minus an exponential. And that is, in fact, what allows us to grow, not shrink. Okay? So there are 3 things you can find on the formula sheet. You can find the charging, 2 charging functions. One is, 2 RC charge functions. One is this one. This is the charging circuit. The other one is the discharging. Okay, it looks like this. So this is the RC charging. That's versus this equation. That's the RC discharging. It's pretty easy to know which one is which. Just look at the function, right? If it's a pure exponential, e to the minus whatever, it'll die, so that's got to be the discharging. And as it will show you, this new function actually grows. So those are the two of the functions, and then the third one is this, and this current function is good for both, right? So that's for both charging and discharging. Eventually, there's no more current flow because you're done either emptying or filling the capacitor. So let's go ahead and look at the details of this charging function. There's some room here. It's really not all that different, it just has that extra 1 in there. But let's try it out. Let's plug in t equals 0. So q at t equals 0, that'll be q full 1 minus e to the minus 0. What's e to the 0, or anything to the 0 for that matter? 1. But notice that 1 minus 1 now gives us 0, which, we knew, right? It starts off empty, okay? Let's try t equals infinity. I'll wait a long, long time. E to the minus infinity, or anything to the minus infinity, right? That's a very large number in the denominator. So what is this? What is it?
Very low.
Yeah. In math class, we talk about limits. In physics, you just say, hey, it's 0. Okay. So now we get 1 minus 0. So that's just a 1. So here we get q full. So this is fulfilling all our expectations. It is growing, right? Because we're taking advantage of the fact that the exponential shrinks, but we're subtracting it from 1, so that actually makes it grow. Okay. So I guess let's try t equals tau again. We learned that tau is an important benchmark. Q full 1 minus e to the minus 1. So e to the minus 1, that's a number, right? E is about 2.7, just shy of 3, right? So it's about 1/3. We learned that it was about 0.37. That's where the 37% comes from. And 1 minus that is just the 63. So it's about 63% of full at t equals tau. So let's draw that function. What does it look like? Here's what it looks like. So the charge starts off at 0, and then at first makes a fairly sizable jump there to try to charge. It's decided to charge at first, and then it starts to slowly charge slower and slower, and it really won't ever reach the quote-unquote full charge until you wait forever. Okay? So that's why we have our tau. Our tau is once again 63%, 37% benchmark. It's used for it's used for exponentials of almost any kind. Okay, and again, while it seems odd to judge why don't we ask how long does it take to fill halfway or something like that? 63, 37%. That's actually a nice number for E. Okay. So once again, tau is the 63%, 37% benchmark. The only difference is that because it's growing, it represents the time it takes to grow to 63% instead of the time it takes to drop 63%, so only have 37% left. Okay? So that's how we often judge one versus another, right? If we had, say, another one that charged more slowly, that also takes forever to charge, but if we're judging these two against each other, this one does take longer to reach this benchmark. Perhaps you're charging through a larger resistor. Remember, tau depends on the circuit. So having a larger resistance that you have to charge through, or having a larger capacitance to charge, means it'll take longer to hit the benchmark. Okay? So that's what that looks like. And once you have that, you can get anything, lots of other things from it. For instance, we know that as goes Q, so goes Vc. So as the charge builds up on the capacitor, so will the voltage. Okay? So let's figure that out. The voltage function will just be the Q function divided by C. So we'll go ahead and put that in. Like that. And what is this thing here? What's Q full over C? Well, generally Q over C is V. Which V is this? It's V full, right? What's the V full? How much voltage can we get on that capacitor? Battery voltage, that's right. So if we were to draw that, voltage versus time, it has the same look. This is V full, this is V across the capacitor. I want to label my y-axis generically as V because I want to include my voltage across the resistor on the same one. The voltage across the resistor, we said, looked like this. We said they traded off, right? And we can see it now with the time axis. Right? Oh, this is a bad drawing. This is supposed to asymptote out of this, and it's like going past it. Like this. There we go. So initially, the resistor takes the whole drop, and the capacitor doesn't have any because it has no charge yet. And by the time you get to the end, the capacitor has all the voltage drop and the resistor has none. By the way, what should be the sum of these two voltage drops at all times? The battery voltage, right? We said that in general, they're in series, so these two have to always add up to the battery voltage, right? We said that the capacitor increases its voltage, but it has to come at the expense of the resistors precisely because Kirchhoff's loop rule has to be obeyed, right? That the sum of the voltage drops has to always equal to 0, which means that the resistor and capacitor have to add up to the battery voltage, right? In fact, you can show, if you plug in both of those functions, which you've got these nice exponential functions, can you see what happens if you add these two up? The exponential part is going to cancel, right? This is going to have this, and this is going to cancel with it. And so it does add up to a constant, which is nice to see, of course. Okay, so I think that does it for this discharging circuit. Are there any questions on that? Yeah.
Does that little section where the two lines cross, does that have any significance?
I'm going to ask you, they're equal. What is the value when they are equal? If they both always have to add up to the battery EMF, this is when they
Are the same?
happen to be equal. That's right. They're covering at 50-50. So that's the point where they happen to have the same voltage drop. But of course, that's just a momentary thing, because if the voltage across the capacitor is going to grow and the one across the resistor is going to shrink, there'll be some point where they meet. It's not particularly significant, but you can infer exactly what the value is here. As far as what time that occurs, that is definitely going to be less than tau, right? Because tau is the time it takes to reach 63% of your eventual, and if you've only reached 50% of your eventual, you're not yet there. So tau would be probably somewhere about here. So tau is the time it takes to reach 63% of your final, not 50%. So that time that they cross is definitely not tau. Okay, any other questions on this? Okay, so when I post homework 4 for you, just be prepared for some of the more tricky math stuff that you'll see. We talked about Kirchhoff's rules with some simultaneous equations needing to be solved, and then this involves exponentials. That's about as difficult as the math really gets in this class. Okay, so they happen to both be on homework 4, so that's why I wanted to have the cutoff for the first exam not include homework 4. Okay, so I'll post that homework for you shortly. You should have a week to do it after you take your exam. It won't be due until late next week. But definitely don't start, last minute. Okay, so that covers the standard RC circuits, charging and discharging. And it actually covers a surprisingly large amount of circuits. So for instance, for our discharging, I'll call it the standard discharging. It looked like this. So we had a capacitor that had been charged up in the past, and then it was going to discharge through a resistor. Now, it's not necessarily just one capacitor and one resistor. It could be discharging through a whole network of resistors. That could be some equivalent resistance, okay? So that's where you use your skills of combining things in series and parallel, right? And it might not just be one capacitor. It might be a whole bank of capacitors that's discharging. And we'll learn how to find C equivalents. So again, I'm pushing off series and parallel capacitors because I think it's some of the easiest stuff and I want to get to the harder stuff first. So our standard discharging equations can cover a whole bunch of capacitors discharging through a whole bunch of resistors. Okay. We just talked about our standard charging circuit. That looks like this. And it needs to not just be one capacitor being charged through one resistor. You could be charging through a whole bunch of resistors, and you could be charging a whole bank of capacitors. I guess you could even put a couple batteries there to do the charging. But even then, even though the equations that I've given you cover a broad range of different scenarios, there are what I'll call non-standard circuits. So, non-standard circuits. So how do you know if you have one of these non-standard circuits? Well, the one thing that we learned is that in both of these types, the current eventually went to 0, right? Eventually, there was nothing left to do. You were either completely done discharging or completely done charging, and there's nothing left to do. And if you have a circuit where the current never goes to 0, then you know right away that you have a non-standard circuit, okay? So, let me give you an example of one. Something like this. And I want to point out what happens here. Even after that capacitor is full, there's still a way around it, right? So the current will never drop to 0 here. So if you see one of these, and you will see one of these, okay, what do? Well, one of the things that we do to make sure that the level of complication in this class isn't too big, you can't give me the time equations, okay? So if I can't ask you at 5 seconds what's going on. So you're going to have to talk in broad strokes. You're going to have to talk about what happens at t equals 0, what happens after a long time, but not at specific times in between. So that is your limited scope on these situations, okay? And here's what I will recommend. These are tools, by the way, that are useful even in the other ones. So these tricks that I'm going to introduce are ones that aren't just limited to these standard things. So let's talk about a capacitor that's completely empty. There's no charge on either plate, and there's no voltage drop across, of course, either. That functionally looks like a short circuit. An empty cap behaves as a short circuit, functionally. Now, what do I mean? I mean, here there is absolutely no impediment for charges to flow, because of course this capacitor is completely empty, right? Completely empty parking lot. There's nothing to prevent the flow, just like along a piece of straight wire. Just like a straight piece of wire, we think of it as an equipotential, right? Well, that's what it is when you have a capacitor that's empty and it hasn't yet had a chance to accumulate a voltage drop. Now, you can't think of it too microscopically. Obviously, there's a difference, right? Here, it's the same charge carrier that shoots from one end to the other, whereas here it's more of a relay race, right? One charge accumulates on the plate and then another positive charge leaves the other one. So, but if you don't think of it microscopically, functionally, that's what's going on. So, for instance, even over here, with the circuit we just finished, at t equals 0, you can functionally think of it like this. So you can functionally replace that empty capacitor with a short circuit. And that helps you really see why the voltage drop across the resistor is the entire battery voltage at first. And in problems like this, if you replace this capacitor with a straight piece of wire, it'll help you calculate what's going on at t equals 0 at the first moment. Okay? The other, of course, other extreme case is what happens when you have plus Q full, minus Q full, and the voltage across the capacitor, of course, is built up to its full value. Okay. Now, I should warn you that in these non-standard circuits, it may not necessarily be the battery voltage. Okay, so watch out for that. You'll see why that is when you start working it out. if this is a full cap, well, functionally, that's like a gap in the circuit. It's a what we call an open circuit. So same deal, no more charges would flow onto a capacitor if it's full, just like no charges can flow through a piece of wire that has an opening or gap in it. So functionally, those two are the same thing. So that can greatly help you analyze as well. Now it's useful over here as well, okay, for our previous circuits. When we get to t equals infinity, what we effectively have is this. So it's very easy to see why there's no current, because there's nothing can get through, right? It's easy to see why the current goes to 0. But over here, we can do the same thing. When this is full, this branch is not being supplied with any current anymore, right? Because it's full up. So all the current will go where? It'll go around, right? So it still has somewhere to go. So no current goes to the capacitor, but it has a bypass around that. And by the way, since you are still going to have current going around this way, there's still going to be voltage drop across here, right? So now the capacitor will be full before it reaches the battery EMF, okay? So this may not be the EMF of the battery in a non-standard circuit. And you'll see that as you start to plug in these things, and you'll find that that's not the case. Okay. So again, for these non-standard circuits, I can't ask you what's happening at 5 seconds. You don't have the equations for that, but you can say what's happening at the very beginning, where oftentimes the capacitor is empty, and it acts like a short. And you can say what happens after a long time when the capacitor is going to fill as much as it's going to fill, and nothing flows to it. Are there any questions on that? Okay, so you have a bunch of these RC questions as well on your homework, and you will be doing a lab on this as well, where you hook up all these things. Okay.